dear children, from reflection we are moving on to refraction. Okay, watch me. This line is called an interface. That means it separates two medium. Like a simple example, that the upper part is air and the lower part is glass. So this line is it's not a line, it's actually a surface which is separating two media. So this is known as an interface. Okay, what will happen if a light ray comes from air, falls like this? We will say this is normal incidence. This is called normal incidence. It is called normal incidence, and it is seen that this light ray will go straight without any change. But there is some change. What is that? The speed of light in air is more than the speed of light in glass. Other than that, there is no change. The light go like this. What happens? The frequency will not change, direction will not change, but the speed will change and wavelength will change. Speed will decrease, wavelength will also decrease. Fine. But what will happen if light comes obliquely? Second case, suppose light is coming obliquely like this. Again I give you this as air, this as glass. Then it is seen that the light will not follow the same path like this. It will not. It will not follow the original path. Rather, it will bend a bit and deviate. It will bend like this. Okay. As a third example, take an interface where this is glass and this is air. Light is slower in glass but faster in air. Say there is a light ray coming like this obliquely. The actual path is this dotted line. But in this case, light will not follow that path, but light will go in this direction. Okay. So from the three diagram, what we understand is that in certain situations, when light go from one medium to another medium, obliquely, there is a change in its path. But if it goes from one medium to another medium, normally there is no change in path. This deviation of light is what we call as refraction of light. And what is the reason for this refraction? It is a difference in the speed of light in the two medium. Because see this. Say there is one interface here, this is air and this is also air. Actually, this is a meaningless thing. Air and air never has an interface between, but assume that there is an interface. I can just think about a plane here separating air above and air below. Light falls perpendicular or oblique, either way. No change in the direction. This light will go straight, this will also go straight. So the deviation is possible. The deviation will happen only when there is a difference in the speed. This is what we call as refraction of light. So how to define a refraction of light? Refraction is the deviation in the path of the light when it enters from one medium to another medium. But one special case, if it enters normally, there is no refraction. So I'll say there is no refraction here, there is a refraction here, there is refraction here. But what will happen if the two media are the same? Then there is no refraction at all, whatever the direction be. Clear? We'll continue its discussion now. Now, if you have two media, you can always classify them into optically rarer medium and optically denser medium. What's the difference? If speed of light is more in one medium, it's called optically rarer medium, and the speed of light is less, then it is called optically denser medium. I am representing R for rarer medium and D for denser medium. So in my first diagram, light is coming from rarer medium to denser medium. Example, air to glass. In the second diagram, it is coming from denser to rarer, just like a glass to air. Okay, what will happen? First point, you need to know how to draw a normal here. This is the interface. I told you interface is a surface. So I have to keep a perpendicular here like this. So I can mark perpendicular. This is the normal. This is normal and this is normal here. Right. Now this is the incident ray. And this incident ray is making an angle here. This is called angle of incidence. And here this is called angle of incidence. Fine. Now, if the light is going from rarer medium to denser medium, it is seen that it is going from rarer to denser means it will not go straight. It will not go straight like this. Rather, it will bend in this direction. So we will say when light go from rarer to denser medium, it will bend towards the normal because this is a normal. It is bending nearer to the normal. So it bends towards the normal, and in this case the light will not go straight, rather that will bend away from the normal. It going from rarer to denser medium, light will bend towards the normal. Here it will bend away from the normal, and this angle made by the refracted ray with the normal is called angle of refraction, and here you can see angle of refraction. So in terms of angle, I can say in this case, in the first case, you can see this angle is smaller than that angle. So angle of refraction is less than angle of incidence. But in this case, angle of refraction is greater than angle of incidence. So technical terms, incident light, refracted light, normal, angle of incidence, angle of refraction. What is angle of incidence? It is angle between incident light and the normal. What is angle of refraction? Angle between the refracted light and the normal. Next we will discuss laws of refraction. There are two laws in refraction. Okay. First law says the normal, incident ray and the refracted ray. This is a normal, incident ray and the refracted ray. All of them lie in the same plane. Incident ray, refracted ray and the normal lie in the same plane. Second rule is also known as Snell's law. And what is that? This angle is called angle of incidence I. This is called angle of refraction R. Okay. Snell's law says that the ratio of sine of angle of incidence to sine of angle of refraction is a constant. Is a constant for a given pair of medium. Okay. What is it? You measure angle of incidence, take sine of that one. Similarly, measure angle R, take sine of that one, take the ratio. This become a constant for a given pair. When the medium changes, the constant will change. Otherwise, that will become a constant. And this constant is called a refractive index. It is called a refractive index of, you call this as a first medium always, they call it as a second medium, refractive index of second medium with respect to first medium. What is it? Snell's law. First law says incident ray, refracted ray and normal lie in the same plane, and the second one says that sin I by sin R is a constant, and that constant is called refractive index, and that is the refractive index of the second medium with respect to the first medium. Okay, these are the two laws of refraction. To understand this better, we will discuss what is the meaning of refractive index. Refractive index will actually tell you, refractive index is written in letter N or as letter mu, but I prefer N, NCERT follows N. Refractive index. There are two types of refractive index that can be defined. One is called absolute refractive index. Absolute refractive index. Absolute refractive index of a medium, to be specific. It is a ratio of speed of light in vacuum divided by speed of light in the given medium. This is normally written in equation form. N equal to speed of light is written as c divided by v. This is the equation for refractive index, absolute refractive index, and we know both are speeds, so this is a unitless number. It is unitless quantity, no unit, no dimension. This is absolute refractive index. And the second one is called relative refractive index. Relative refractive index of one medium with respect to another medium. One medium with respect to another medium. This is written as n/1. What is n/1? I'll say one medium, that means medium 2. Medium 2 with respect to another medium 1. It's always in that order. Okay. So n/1, refractive index of the second medium with respect to the first medium. This is given by ratio. This is given by speed in the first medium divided by speed in the second medium. It is a ratio of, just like this one, speed of light in the first medium by speed of light in the second medium. You can see that this is also unitless number. Absolute and relative refractive index. Fine. From the absolute refractive index, what is the value of V here? What is V in the first case? What is V? How to get V? V equal to C divided by N. If V equal to C by N, then we can say V1 will be equal to C by N1, where N1 is the absolute refractive index of the first medium, divided by V2 will be V2 equal to C by N2. So this gives you C and C cancel. This gives you N2 divided by N1. So relative refractive index has got two equations. One, it is either V1 by V2, where V1 and V2 are the speed of light in the two medium. Otherwise, it is N2 by N1. From this, we can continue further. What is N12? N12. I told you N21 is the refractive index of the second medium with respect to first one. So what is N12? It is the refractive index of the first medium with respect to the second medium. This will be written in the same manner. This will be written as V2 divided by V1. Aha, that's nice. It is a reciprocal of that one. So this can be written as N1 by N2. Again reciprocal of that one. So I can say N12 is nothing but 1 by N21. Important relation. N12 is equal to 1 by N21. Arey wah. That's a beautiful relation. Now if I say NGW, what is it? What is the meaning of NGW? G for glass, W for water. So this is a refractive index of glass with respect to water, and this is nothing but 1 by refractive index of water with respect to glass. How to calculate NGW? NGW, you follow this equation, NGW equal to NG by NW. This is N glass by N water. Okay, you can just manipulate them like this. Now what is the actual value of NG and NW? It is seen that it is calculated that for most of the glasses, refractive index is 3 by 2, 1.5 for most of the glasses, and for water this is approximately 4 by 3. It is approximately 4 by 3. So N glass with respect to water is 3 by 2. So you can see that this will be equal to 3 by 2 into 3 by 4. So this gives you 9 by 8. Refractive index of glass with respect to water is 9 by 8. Therefore, refractive index of water with respect to glass will be reciprocal of this one. That will be equal to 8 by 9. So what we discussed so far are these points. What are they? We were discussing laws of refraction. First law, second law is also known as Snell's law, and that gives you sin I by sin R is a constant. That constant is called the refractive index of the second medium with respect to the first medium. And what is refractive index? Refractive index is the ratio of speeds. If you want absolute refractive index, you take speed of light by speed of the light in medium, speed of light in vacuum by speed of light in medium. If you want relative refractive index, you take speed of light in one medium and speed of light in the other medium. And one important relation that we saw is that N12 is a reciprocal of N21. That's what we applied here. N glass with respect to water is a reciprocal of N water with respect to glass. And the refractive index of glass can be approximately taken as 3 by 2, and for water it is approximately 4 by 3. You can calculate them like this. Okay. Now we will discuss refraction in a glass lab. Before that, see, we will be using Snell's rule here. And what was Snell's rule? We studied that sin I divided by sin R equal to refractive index of the second medium with respect to the first medium. This is normal method of writing Snell's rule. But in such derivations, it is better to convert this into a different format. What is that format? N1 sin I equal to N2 sin R. This is a form that is easy for you in derivations. I tell you why. Consider a glass lab. There is a light ray incident. This is the incident light ray. This light ray would have gone straight in the if the slab were not there. But due to the presence of slab, this is air, this is glass, the light ray bent towards the normal. From glass to air, it bends away from the normal. Two refractions, one at A, another at B. Right. This is the actual path of the light, but this is the new path of the light. We can apply Snell's rule in this form at A as well as at B, and we will prove something. What is that? See this. I will write at point A. At point A, I have N1 and angle I. I will write N1 sin I equal to, what is the refractive in the second medium? That is N2, and angle is R1, N2 sin R1. That is at point A. At point B, what can I write? At point B, the incident angle is R2. Incident angle is R2. So I will write N2 sin R2 equal to, what is outside? Outside again I have air, that is N1 sin E. N1 sin E. Clear? But you should know, a glass slab has got parallel sides, and this line, the ray passing through the slab is actually a transverse. Therefore, angle R1 should be equal to angle R2. R1 and R2 must be equal. What does it mean? N2 sin R1 must be equal to N2 sin R2. So this term over here, this term over here, and this term over here are equal because R1 equal to R2. So what happens? N1 sin I should be equal to, so let N1 sin I should be equal to N1 sin I is equal to N1 sin E. So which implies angle I is equal to angle E. So in a glass slab, when a light ray passes, what happens? It will undergo refraction at point A and refraction at point B, but this angle I and this angle E will be equal. So what happens? The incident ray, this thing, and the emergent ray, this thing, will be parallel to each other. Incident and emergent ray will be parallel. So the direction of the light will not change. This light was going in this direction. This light is also going in the same direction. There is no change in the direction. There is no deviation. Only a lateral displacement. Instead of going in that way, it is going in this way. There is only a lateral displacement. So this is refraction in a glass slab. As an application of refraction, this is a common experience that if you look into a swimming pool, the bottom of the swimming pool appears to be raised a bit. The depth actually appears to be less than the actual depth. That's why we have two terms, real and apparent depth. Okay, we will prove it like this. We will consider a glass slab or a water body, a transparent medium. This is a medium. It can be a glass slab on a paper, or it can be water in a swimming pool. This is the top surface, this is the bottom surface, right? Assume that from the bottom point, one light ray is coming perpendicular upward, and we know this is called normal incidence, and at that point there will be no refraction. At this point there is no refraction, the light will simply come out. But what happens if another light ray comes obliquely here? This is water and that is air. So this is a denser medium, that's a rarer medium, light will bend away. And here you can draw a normal. You can draw a normal here. You can draw a normal here, and we see that this is angle of incidence and this is angle of refraction. And from the diagram we can see this angle will be equal to this angle I, and this angle R will appear here. I marked incidence and refraction angles. Fine. Now, for an observer outside, this light ray will be appearing from this point. Okay. So I marked bottom point A, top point B, this as C, this as D. And for observer very close to normal, because this is a normal. For an observer very close to the normal, that is an important point. For observer very close to normal, that's a point you should know. Observer very close to normal. All angles will be very small. Okay, then I can write a sin theta can be written as tan theta. That's a point. Sin theta can be written as tan theta for small angles. Okay. Now I will define. I'll define Snell's rule. What is Snell's rule? I can define Snell's rule at this point C. So I can say at C, angle of incidence I, and I will call this as refractive index N1, this as refractive index N2, because normally we will take air as the first medium, water as the second medium. Then I can write N1 sin R equal to N2 sin I. That's it. N2 sin I, N1 sin R. And I know sin theta equal to tan theta, so I can write this as N1 tan R equal to N2 tan I, because angles are small. So N1, what is tan R? What is tan R? This is tan theta, this is R. Tan R is opposite side BC by BD is equal to N2. What is tan I? This is I in this triangle, that is BC divided by AB. We can see that this BC and this BC will cancel. Okay. Now what I am getting is, I will get N1 divided by BD. What is BD? BD is the apparent depth dA. So N1 by D apparent is equal to N2 divided by, what is AB? AB is the real depth dr. Here you have n1 and n2. You have n1 and n2. Just to define n2 by n. What is n2 by n1? n2 by n1 is a refractive index of this medium with respect to air. n2 by n1 is equal to d, n2 by n1 equal to d real divided by d apparent. But we also know that n2 by n1 is the refractive index of the second medium with respect to the first medium. Comparing these two, I will get d real by d apparent equal to n21, and I want d apparent. So from this I will get apparent depth is equal to the real depth dr divided by refractive index n21. So how to calculate apparent depth? You have to divide the real depth by the refractive index. Fine. Now one more point can be asked. What is it? The bottom was here. Now but see, every point on the bottom will appear here. This is where the floor of that pool will appear. So the floor has gone upward by a value s. This is called the shift produced by refraction. And how to do this? How to calculate this shift in the bottom? We can say the bottom shifted, the shift can be calculated. Shift s is what? What is actually shift? Shift is nothing but real depth minus apparent depth. It is real depth minus apparent depth, which can be written like real depth minus apparent depth is nothing but real depth divided by n21. So this is d real bracket 1 minus 1 by n21. 1 by n21. So this is the equation for the shift of the bottom. So what we derived? The equation for the apparent depth and the equation for the shift of the bottom. Two important points. Shift and apparent depth. Hope it's clear. So my dear students, we have done basics of refraction and reflection so far. Now we have more scintillating things to be explained in the class. It's called atmospheric refraction, total internal reflection, and sort of other things. We'll be doing that in the next class. Till then, bye.